Hi, today we will discuss about one of the most important as well as one of the most confusing topic of operating system, that is process synchronization. Okay, in every year you will get at least one question from this topic, and unfortunately students find this topic very difficult, so mostly they leave this topic. But you don't worry, you just keep watching my videos, and I'm sure that it will be very beneficial for you. Okay, you just watch my videos completely, and I'm sure after that you will be able to solve all the questions. And don't worry, we will solve all the questions here. Okay, so let's start with process synchronization. Okay, process synchronization. And before this, I would like to give you a brief overview of interprocess communication. Okay, so what is interprocess communication? As the name suggests, it means what? In a system, several processes run. So all these processes, what they do, they communicate with each other. They talk to each other. They sometimes they access same location, same variable. Okay, so that's all about interprocess communication. Here, there is nothing to know much. Okay, so I tell you one thing that if several processes are communicating with each other, then how they are communicating? So they are communicating through shared memory. Okay, shared memory is a region which is being accessed by lots of processes. Okay, so if lots of processes are involved, if lots of processes are involved to access a particular shared region, then there is a chance of data inconsistency. Are you getting it? There is a chance of data inconsistency if there are lots of processes are involved to access the shared region. Okay, I think rather than telling you much, I should explain you it in a better way. Okay, you just see here. Suppose there are two processes, process P1 and process P2. Okay, these two processes are there. Process P1's task is to increment, and process P2's task is to decrement. Fine. Process P1's task is to increment, and process P2's task is to decrement. Increment, this is an increment operator. It means what? It will do +1, and it's a decrement operator. It do -1. Okay. So suppose in a memory location, suppose in a RAM, it's a memory. At this particular location, say there is a value stored at this particular location, say 5. Okay. So now what process P1 will do? Process P1 will access this, and process P1 will modify the value of 5. Okay. So how it will happen? Initially CPU will be with process P1. Okay. So it means what? Process P1 will perform its task. How process P1 will perform? Process P1 will first read the value at this memory location. Just listen it carefully. What process P1 will do? First, process P1 will read the value. What's the value present in this location? So what process P1 will do after that? When P1 will get to know, okay, the value is 5. So process P1 will increment it. It will make it 6. As the task of process P1 is to increment. So process P1 has incremented the value to 6. Fine. Now, CPU is switched to process P2. After process P1 finished its task, CPU is switched to process P2 here. Okay, and you see what's the task of process P2? Decrement. Okay, so what process P2 will do? Process P2 will now first read the value. Listen it carefully. What process P2 will do? Process P2 will first read the value, and process P2 will find it as 6. Okay, then process P2 will ultimately, since it's a decrement operator, process P2 will ultimately decrement the value of 6 to 5 again. Okay, and after this, both the tasks, you see now the value has finally became 5, and both the tasks has successfully completed their operation. Initially the value was 5, then process P1, what it did, it just added 1 to it. Okay, and after that, when CPU was given to process P2, what process P2 did? P2 decremented decremented 1 from it. So ultimately, this 1 cancel and we got 5 as the final value. So no problem is there. We are getting the desired result. It's not incorrect. Data is consistent here. Okay. So you see, it's so simple. But I've already told you, but there is a chance of data inconsistency when the two processes communicate. Okay, through a shared region. Here you say this is a shared region. This is a shared region. Shared region. Why? Because here you see this region is being shared by process P1 and P2. Process P1 and P2 both are accessing this region. Okay, but now I am going to tell you how the result can become inconsistent. Okay, so just focus here. Should I rub this? Okay, I think I should write here. Okay, you see, there are two processes. Okay, just watch it very carefully. P1 and P2. Okay, and the task of process P1 is same, increment, and process P2 decrement. Okay, now you see here what will happen. Say there is a count variable. There is a count variable. Okay, and the value of count variable is 5. And both process P1 and process P2 can access this variable. Okay, this variable can be is being shared by process P1 as well as process P2. Okay, are you getting it? Now you see. So I'm writing the code for P1 and P2, and after that I will explain it. Okay, so you see here, process P1 will execute its instruction number 1. What's instruction number 1? Move count, comma, R1. Don't worry, I will explain you each and everything. Then R1 plus plus. Then third instruction is move R1, comma, count. Okay. So it's a code of process P1. So let me write the code of process P2. Move count, comma, R2. Okay. Let me rub this. Now, okay, it's a first instruction. Okay, it's a first instruction of P2. And the second instruction is R1, R2 minus minus. Why? Because this P2 is performing decrement operation. And its third instruction is move R2, comma, count. Okay. So now, let me explain you. Suppose CPU is with process P1. Okay. Now CPU is given to process P1. So how process P1 will perform its operation? You see, you just see the first instruction: move count, comma, R1. So R1 is a register which is only accessed by process P1. Okay. So let me write here R1. Is it visible? Okay. R1. Okay. So now what processor P1 will do? It will move the value of count, or you can say it will copy the value of count, and that copied value will be moved to R1. So now since the value of count is 5, so this value will be moved to register R1. So now register R1 contains 5. Okay, fine. So its second instruction is R1 plus plus. It means what? Increment the value of R1 by 1. So it means what? 5 will be incremented to 6. Fine. And you see after third instruction, you see move R1 comma count. It means what? This incremented value should be moved to the count. So now since the incremented value is 6, so it will be moved to the count. So now count will contain 6. Simple. Here you see process P1 successfully finished its 1, 2, 3. All the three instructions. Okay. Now suppose since process P1 has completed its task, so now the CPU is given to process P2. Now CPU is with process P2. Okay. So what process P2 will do? So you see here it is written move count comma R2. It means what? Process P2 will move the value of count to a register R2. Here R2 is a register which is only accessed by process P2. Okay. So now now R2 will contain 6. Because what actually happened? Process P2 first read the value of this variable. It is 6 as it was updated as 6 by process P1. So P2 got to know that yes, the value is 6. So now P2 will move this value to its register R2. So R2 contains 6. So second line is R2 minus minus. That is R2 decrement. So the value will be decremented to decremented by 1, so the new value is 5. Okay. Now third line will be executed. Move R2 comma count. So now this value will be stored to count. Okay. So the count contains 5. So till now you see everything is fine. Till now the data is consistent. You see what actually happened? 5 plus 1 is performed by process P1. So the value became 6. And what process P2 did? P2 did minus 1. So the value ultimately became 5. So till now no problem is there. Okay. Even you start here in this case, CPU was first given to process P1. And after that CPU was given to process P2. And even if you start from process P2 and you just process P2 starts first. I mean to say that even process P2 completes its whole instructions. After that, process P1 execute. Then also there will be no problem. Okay, let me show you how. You see here, the value of count is suppose 5. Okay, and suppose now CPU is given to process P2 first. In the previous case, CPU was given to process P1 first. So here what's happening, you see, move count comma R2. So the value of 5 is moved to R2, 5. R2 minus minus. So the value of R2 will become 4 due to decrement operation. Move R2 comma count. So this value 4 is moved to count. So now the value of count is 4. Fine. Okay. Now there is a context switching and CPU is given to process P1. So what process P1 will do? See here. Move count comma R1. So process P1 will first read the value of count, and process P1 found that the value is 4. So what process P1 will do? It will move the value of count to R1. So R1 will contain 4. Okay, then second instruction R1 plus plus. So now it will become 5. And you see the third instruction, move R1 comma count. So this value 5 will again move to count. So 4 will again become 5. So the final value is 5 once again. So you see, even when P2 started first, still we got a consistent result. I mean to say correct result. How it all happened, you see, here since P2 started, so initial value of count was 5. Then what P2 did, P2 decremented the value. So the final updated value of count became 4. And after that, when CPU was given to process P1, what process P1 did? Process P1 just added 1 to this updated value of count. And finally, the value of count became 5. So everything is okay till now. But suppose if there is an interleaving happens between the two processes, then there are chances of data inconsistency. Interleaving, or you can say if the process is preemptive, if the process gets preempted, then there are lots of chances of data inconsistency. So now just watch it very carefully. Now I will show you how the data will become inconsistent. Okay. So till now, what I have shown you is a very clear case. Here there is no interleaving happening, because if a process is fully completed, after that CPU is given to another process. So no problem at all. But now I am going to show you, if there is interleaving happens or there is preemption happens, how it affects the data, how it affects the entire result. Okay, you just watch it very carefully. So you see the value of count is 5, and now suppose CPU is with process P1. Okay, now you see what process P1 will do. Process P1 will execute its first line. Process P1 executed its first line. So process P1 read the value of count as 5, move count comma R1. So process P1 moved the value of count to R1. So now R1 contains 5. Okay. So after this, process P2 will execute line number 2. Process P2 will execute its line number 2. Here what will happen? R1 plus plus. So it will become 6. Okay. So the register R1 contains 6. Okay. But before process P2 executes line number 3, a preemption happens. Okay. A preemption happens at this point. And now CPU is snatched from process P1 and given to process P2. Okay. Now you see here CPU is with process P2. Okay. So I repeat, process P1 executed its first line, second line, and before process P1 could execute its third line, interleaving happened, and the CPU is given to process P2. Okay. So now you will see what will happen. Here you see process P1 could not update the value of the count variable. Why? Because due to preemption. Okay. If process P1 could have updated the value of count variable, then here it would be 6, not 5. But unfortunately, the CPU is given to process P1. So process P2. So you see what process P2 will do. Process P2 will execute its first line. So here I will write P2.1. So in the first line, what process P2 will do? Process P2 will read the value of count as 5, not as 6, because the value was not updated by P1. Okay. So process P2 will read the value of count as 5, and now it will move the value of count to R2. Okay. So now R2 contains 5. Okay. In the now process P2 will execute its second line. Means P2.2. Okay. So in the second line there is a decrement, 5 to 4. So the value got decremented to 4. Okay. And you see after this process P2 executes its third line, P2.3. So what is third line? Move R2 comma count. So the value of R2 is moved to count. So count will contain 4. Okay. So the value of the count is 4. So process P2 completed its all the tasks. Now again there is a preemption. Okay. Now the CPU is given back to process P1 again. Okay. So now process P1, since process P1 has already completed its instruction number 1 and 2, so it will start from instruction number 3. Okay, so here P1 will perform execution of instruction number 3. Fine. Now here you see, Now here you see, move R1 comma count. So process P1. So what's the value of R1? It is 6. So what process P1 will do? Process P1 will move this value of 6 to count. So now count contains 6. So now you can see the inconsistency. So can you understand it? Initially the value was 5, and after increment and decrement operation, the value was expected to be 5 again. 5 plus 1 minus 1. What's the final value? 5. But here you see, here there is 6. So we can say that the data is consistent. So how this happened? Due to interleaving. Because here you see, at line number 2, the process got preempted and CPU was given to process P2. Before P1 could update the value of count, the CPU was given to process P2. So this created a trouble. Okay, and ultimately we got a value of count as 6. Okay, I write here the value of count that we got as 6. But what was the expectation? We were expecting the value of count to be 5, but unfortunately it's 6. Okay, now you see, now you see this value. Suppose so here the order of execution was like that: 1, 2. Process P1 executed its first instruction, second instruction, preemption. Then process P2 executed its first instruction, second instruction, third instruction. After that preemption, again process P1 executed its third instruction. So the count value is 6. But suppose if the order of execution, I change the order of execution, then will it affect the result? Let's see. So let's start from the beginning. Now suppose here you see the value of count is 5. Okay. Now suppose CPU is with process P2 now. Process P2 starts first. Okay. So you see what will happen. So process P2 will execute its line number 1. Okay. So what will happen? Process P2 will read the value of count as 5 and will move it to register R2. So register R2 contains 5. Fine. After that there is a decrement operation. You see. So now process P2 will execute its second instruction and register R2 is now 4. 5 is decremented to 4. Okay. And here you see, before process P2 could execute the third instruction, or you can say that before process P2 could update the value of count as 4, there the interleaving happened at this point. Okay. At this point interleaving happened and now CPU is snatched from process P2 and given to process P1. Now CPU is with process P1. Okay. Now here you see what's happening here, you see. So Yes. So P1 will execute line number 1. So P1 will first read the value of count. What's the value of count? 5. As the value of count was not updated by P2 due to this interleaving, so P1 will read it as 5 because the value is 5. So P1 will execute line number 1. P1 dot 1. So in line number 1, P1 will move the value of count to register R1. Here is 5. Okay. So now P1 will perform its line number 2, R1 plus plus. So it will become 6. Register value will become 6. Okay. And P1 will execute its, so it will be P1 comma 2. And P1 will execute its line number 3. It's what's written? Move R1 comma count. So this value will be moved to the count. So now count contains 6. Okay. So P1 successfully finished its task. Okay. Now CPU will be given to process P2. So now CPU is with process P2. And you see here, since process P2 has completed its instruction number 1 and 2, so process P2 will execute its third instruction. So process P2 will execute its third instruction, move R2 comma count. So what's the value of R2? 4. Now it will be moved to the count. And now count contains 4. So you see, if we follow this order, we get the value of count as 4. Okay. So just see, we are getting different results due to the different order of execution of processes. And these are inconsistent result, incorrect result. These are undesirable result that we don't desire. So why these things are happening? Due to the interleaving between the processes. Okay. So this condition is known as race condition. It's a very important term, race condition. Okay. So now let me write the definition of race condition. Okay. I think you have clearly understood what I mean to say. Okay. Actually, what happens in race conditions when more than one process they cooperate, or you say they compete. So this they compete through a shared memory, then this may lead to data inconsistency. Okay, and this is called race condition. And the output value of the race condition totally depends upon the order of execution of the processes. Here you see why I have used the term compete. You see here when process P1 was running initially when process P1 was running, then P2 was in a hurry. So before process P1 could finish its task, P2 snatched the CPU from process P1. Okay, so you see process P1 here could finish its task. P2 got the CPU. P2 didn't wait for P1 to finish the task. No, P2 was in a hurry. P2 was in a competition mode. Okay, that's why we got inconsistent result. Same thing happened here. Here you see before P2, in this order of execution, before P2 could complete its task, P1 was in a hurry. P1 was in a competition mode. So P1 snatched the processor from process P2 and P1 started executing its own instruction, which ultimately led to data inconsistency. Here we got 4. Okay, so this is a race condition. So let me write the definition of race condition. So now write down this. So I read it out for you. Race condition. So I've already explained you about the race condition. You just write it. When two or more processes want to cooperate or compete through shared memory, this may lead to data inconsistency. As you have seen in the example of process P1 and process P2 that I have given, okay, here what was happening? Here when process P1 started execution, then P2 didn't wait for P1 to complete the execution. It ultimately snatched the CPU from process P1 and started executing its own instruction, and ultimately that led to data inconsistency. Okay, and you see here the value of output depends on the order of execution of the process. I have already given you the example how the order of execution of process affects the output. You will get different values in the result. Okay, if P1 is executing, then there is a preemption, and P2 got the CPU. Okay, and the value which will be produced at the end, it will be completely different from the execution in which P2 will start and there is a preemption and P1 got the value. Okay, so I've already given you the example. I hope you have understood it. So this is all about race condition. Okay, so now you see process synchronization. I've written a process synchronization. So it is a technique used to avoid RC. RC means race condition. So process synchronization is a technique which is used to avoid this type of conditions, that is race conditions. So with the help of process synchronization, we avoid data inconsistency. So here what happens when one process is accessing the critical section? Critical section means what? It is a part of a code where the shared resources are accessed by different processes. Like in the previous example, you see count variable. Okay, it was just a simple example. Count variable, it was shared. It was being utilized by process P1 and process P2 at the same time. Okay, so that's what I have written. It is a technique used to avoid race condition. Here, when one process is accessing the critical section, other process is not allowed to enter in it. When one process is accessing the critical section, means the other process is not allowed to enter in it. Means what? In the previous example that I have given, in that example, you see when process P1 was accessing the count variable. Okay, when P1, then if process P2 didn't interfere in it, then the ultimate value was okay. The ultimate value was correct. I mean to say that P1 fully completed its task. After that, if CPU is given to process P2, okay, then there won't be any problem. So that's what I have written. When one process is accessing the critical section, other process is not allowed to enter in it. When P1 is accessing the count variable, P2 should not disturb it. P2 should wait till process P1 completes its execution. Okay. So if these things are followed, then we will get consistent result. Okay. And it's a definition of critical section. It is a part of the code where shared resources are accessed. I've already explained you. Okay. So I think you got the meaning of race condition, process synchronization, and critical section. But you see, implement process synchronization is not very simple. Here we have to consider certain issues. Okay. Here we have to consider some conditions. Okay. And also we have to deal with certain trade-offs. Okay. That I will explain you in the next video. Okay. Thank you.